Today we're going to see chapter 10. The chapter is about circle, and what we're going to see in the chapter is about tangent to a circle. Okay, now look at this. Okay, I've drawn three figures. Now in the first figure, we have a line and a circle, and the line is not touching or cutting the circle. In the second figure, we have a circle and a line, and the line is cutting the circle at 2 points A and B. And in the third figure, we have a circle and a line, and the line is touching the circle at 1 point. Now, if the line cuts the circle at 2 points, then that line is called a secant. That line is called a secant. And if a line touches the circle at 1 point, then that line is called a tangent. Okay. And in the figure 1, it is not cutting, it is not touching. So it is just a line and a circle. We don't have a special name. But in the second figure, the line is cutting the circle at 2 points, A and B. It is cutting the circle at 2 points A and B. So that line PABQ will be a secant. And in the third figure, the line PQ is touching the circle, not cutting, just touching the circle at a point. Such a line is called a tangent. So in this chapter, we are going to see about tangents only. Now, in a circle, at a point, we can draw only one tangent. At a point, we can draw only one tangent. Okay, at a point on a circle, we can draw only one tangent. But we can draw many tangents on the circle at different points. So for a circle, how many tangents can be drawn? It will be infinite. But at a point, how many tangents can be drawn? Only one. Next, at a point, how many seconds can be drawn? At a point, we can draw many seconds. Second is a line that cuts the circle at 2 points. So at a given point, we can draw many seconds. Infinite seconds we can draw. Okay, but among them, only one will be a tangent. One will be a tangent, and we can say that tangent is a special secant, in which 2 points coincide at 1 point only. So once again, I'm repeating. For a circle, at a point, how many tangents you can draw? Only one. But how many seconds we can draw? Infinite. Now, on a circle, how many tangents you can draw? We can draw infinite tangents at different points. At different point, we can draw infinite tangents. Okay. Okay, now we'll see theorem 10.1. The theorem is the tangent at any point of a circle is perpendicular to the radius to the point of contact. So this question may come as a question also. So instead of writing theorem, we can write prove that the tangent at any point of a circle is perpendicular to the radius through the point of contact. Okay, so we are going to prove it. So let's take it. Say we have a circle and we have a tangent. So let PQ be a tangent at a point A. And according to this theorem, what is the proof? If there is any tangent to a circle, then radius drawn through the point of contact will be perpendicular. So that means tangent and radius will be perpendicular. Okay, look, we have a tangent at A. The point where it is touching the circle, that point is known as point of contact. That point is called point of contact. The point where the circle touches, where the tangent touches the circle, that point is called point of contact. Now at the point of contact, we'll draw a radius. And according to the theorem, we have to prove that the radius and tangents are perpendicular to each other. So write this and draw the figure, and we'll write the given. We'll take a circle with center O. And PQ is a tangent. At A. And to prove what? The radius. Okay, we'll mention the radius also. OA is the radius. To prove what? OA perpendicular PQ. Okay, write this and then just raise a hand because I need to rub it. Okay, fine. So let me rub the first part, then we'll start the proof. Okay, for this we need a construction. Construction will be, we'll take a point, say, we'll take a point we'll take a point, say C, or say B. We'll take a point B on PQ and let it intersect, and we'll join OB to intersect the circle at, say, C. Take a point B on AQ other than A, not AQ, PQ. PQ, take a point B on PQ other than A, and join OB to intersect the circle at C. Okay, so it is intersecting the circle at C. Okay, now we'll show the proof. Okay, first, let's see. If you see OA is radius and OC is also radius, so they will be equal. OA equal to OC. Mark it 1. Okay, then we can take OB as what? OC plus BC. OB, we can take it as OC plus BC. Okay, so instead of OC, I can write OA. Why? Because I've shown them equal in 1. So that means what I'm getting, OB is equal to OA plus BC. Now, since OB is equal to OA plus BC, that means each of them, OA and BC, will be less than OB. So therefore, what you can take, OA less than OB. OA will be less than OB. So what is, and if OA is less than OB, what does it mean? That means what? OA is shorter than OA is shorter than OB. Now, in the same way, what you can show is in the same way we can prove that OA is the shortest line segment OA is the shortest line segment among the line segment drawn from okay, I need some more space, so I'll be rubbing the first part. So in the same way, we can prove that OA is the shortest line segment among the line segment drawn from O to the line PQ. So therefore, we can take OA perpendicular to PQ. So what you have shown is here, OA is the shortest line segment drawn from O to PQ, and the shortest line segment drawn from a point to a line would be always a perpendicular. If you have a line and a point, the shortest line segment that you can draw from a point to a line will be always a perpendicular. So from this theorem, we can, if there is a tangent and if there is a radius at the point of contact, then we can take always each of them perpendicular to each one. So if you have a tangent and a radius at a point of contact, then we can take radius perpendicular to the tangent, or tangent perpendicular to the radius. Okay, once you're done, raise your hand. Some more hands. Okay, fine. Now we'll see the exercise 10.1. Okay, question number 1. How many tangents can be drawn to a circle? Infinite. You can just write it in your book. How many tangents can be drawn? How many tangents can a circle have? Infinite. Then 2, 1. A tangent to a circle intersect it in 1 point. In 1 point. Then number 2. A line intersecting a circle in 2 points is called a secant. Then number 3. A circle can have 2 parallel tangents. A circle can have 2 parallel tangents. Say, if we have a circle, then how many parallel tangents we can have? We can have only 2 parallel tangents. We can have only 2 parallel tangents. A common point of a tangent to a circle and the circle is called point of contact. The common point between the tangent and the circle is called the point of contact. Okay, then we'll say question number 3. The question is, a tangent PQ at a point P of a circle of radius 5 meet a line through the center O at a point Q, so that OQ is 12 cm, the length of PQ. PQ is a tangent, you have to find the length of PQ. So we have a circle, and PQ is a tangent at Q. PQ at tangent PQ at a point P. Oh no, sorry. It is a tangent at P. So Q will be here. Then the radius is 5. So center is O, and OQ is 12. And the radius, if you draw at the point of contact, that is 5. You have to find the length of PQ. Okay, so given is what? A circle with center O. Whenever there is a circle, we have to mention the center. A circle with center O. So if there is a circle, first we have to mention the circle with center. So a circle with center O, our center is O. Then PQ is a tangent. At what point P? Then OQ is given 12. And the radius OP is given 5. Okay, then to find what PQ. Okay, here. Okay, say first this angle will be 90. Angle P will be 90. Why? Because tangent perpendicular to radius. Angle P equal to 90. Why? Tangent perpendicular to radius. So if angle P is 90 in triangle OPQ, what you can do? We can use Pythagoras theorem and we can find the third side. So in right triangle OPQ, what you can do? We can apply Pythagoras theorem. OQ square will be equal to OP square plus PQ square. Now put the value. OQ is 12, OP is 5, and PQ is, we're going to find, we're putting the value from given. Now just solve this. Now 12 square is how much? 144 equal to 5 square is 25 plus PQ square. Now whatever you're going to find, we'll keep it on the same side. PQ is on the right, so keep it on the right. And take this 25 to the other side. First write what is on the other side, then take this 25 plus will become minus. Now 144 minus 25 will be how much? So 119. So PQ square, we're getting 119. Now find PQ. From PQ square, how to find PQ? We'll take root on the other side. So we're getting what? Root of 119. Now root of 119, we cannot find the prime factor. So because it is a prime number, so we can write PQ is root of 119 cm. So answer is option D. Okay, if you're done, you can raise your hand. Some more hands. Okay, fine. Now, question number 4 is not important, so I'm not doing. Then we'll see theorem 10.2. Before that, now say we have a circle. Now from a point outside the circle, say we have a circle. So from a point outside a circle, how many tangents can be drawn? We can draw 2 tangents from that point. From any point that is outside the circle, from that point we can draw 2 tangents. So from an external point, we can draw at the most 2 tangent only. We can draw at the most 2 tangent only. Okay, now we are going to say something about this only. That is theorem 10.2. Now this theorem also we need to prove it. So I'll take it in terms, I'll take the theorem as prove that the length of the tangent, tangents drawn from an external point to a circle are equal. So the theorem is what? From an external point, if you draw tangents, then the length of the tangents are equal. Now we have seen what? From an external point, say P, we can draw at the most 2 tangents, say at A and B. And by this theorem, what you can take? We can take PA and PB equal, or AP and BP equal. The length of the tangent, we can take it equal. The length of the tangent is what? This and this, AP and BP, or PA and PB. Okay, now we are going to prove this theorem. So let's take it. Given is what? A circle with center O. So we are going to take a circle with center O. PA and PB are tangents. PA and PB are tangents. At A and B. Then to prove what? Okay, P and PB are tangents from some instead of taking A and B, P and PB are tangents from the same external point. Same external point P at A and B. So P and PB are tangent from the same external point P at A and B. And to prove what? PA equal to PB. Okay. To prove this, we need construction. We'll join this OP. We'll join OA and we'll join OB. So construction will be join OP, OA, and OB. Okay, next we are going to prove Okay, if you're done, you can raise a hand. I'm going to rub the first part. Okay, so I'm going to rub the first part. Then we'll start the proof. Okay, proof. Now to prove this, what you have to prove is PA and PB equal, and PA and PB are what? PA is a part of triangle AOP, and PB is a part of triangle BOP. So we'll try to show these two triangle congruent. So we'll take in triangle AOP and triangle BOP, and we'll try to show that they are congruent. Now how to show they are congruent? Now look, we have a tangent. AP is a tangent, or PA is a tangent, and OA is the radius. So tangent and radius will be perpendicular. Again here, PB is a tangent and OB is the radius. So again, it will be perpendicular. So angle A and B are both 90 each. Then hypotenuse is common, and this OA and OB are both radius, so they will be equal. So what are you getting? Right hypotenuse side of one triangle equal to right hypotenuse side of the another one. So the triangle will be congruent by RHS. So we're going to show that these two triangles are congruent by RHS congruency. In this two triangle, one angle is 90. Angle A equal to angle B equal to 90. Why angle A and B are 90? Why? Since tangent is perpendicular to. We have shown in the last theorem. We have already proved. Then we can take OP equal to OP. They are both hypotenuse and they are, is common. And again, we have OA equal to OB. Why they are equal? They are both radii of the same circle. Radius of the same circle are equal. So radii. Plural of radius is radii. So they are radii of the same circle. So what are you getting? One angle 90, hypotenuse are equal, and one side equal. So right hypotenuse side. So the triangle AOP is congruent to triangle BOP by what congruency? RHS congruency. And since they are congruent, we can take therefore PA equal to PB by CBCD. And what does CBCD means? Is corresponding part of congruent triangle. We have done in class 9.